On July 1st, 2025, the scientific community was stunned when an interstellar object named 3I Atlas was discovered. NASA's initial estimate of the object's size was cautious, to say the least. The object's nucleus was thought to be somewhere between 440 meters and 5.6 kilometers across, a range so wide that it left scientists scratching their heads. The uncertainty surrounding the size of the object was immense. Nobody knew for sure what they were dealing with, and the excitement was mixed with a sense of awe and uncertainty. But things began to change with the arrival of the post-perihelion data. From December 2025 through January 2026, Hubble provided crucial observations that allowed astronomers to peer through the bright coma of gas and dust surrounding the nucleus of 3I Atlas. This coma had previously made it impossible to directly measure the object. However, by carefully subtracting the coma's glow, scientists could isolate the faint signal of the solid nucleus beneath. What they found was nothing short of remarkable. The true size of the nucleus was confirmed to be 2.6 kilometers in diameter, with a margin of uncertainty of about 0.4 kilometers. This new measurement was a turning point in our understanding of the object. To put the size into perspective, the nucleus of 3I Atlas was roughly the length of the famous Big Ben to Tower Bridge in London, or the width of Madrid's Retiro Park. Yet, this was no ordinary object. It had been traveling through interstellar space for over 7 billion years, only to pass through our solar system for a mere 8 months. Avi Loeb, one of the astronomers studying 3I Atlas, immediately grasped the implications of this discovery. With a diameter of 2.6 kilometers, the mass of 3I Atlas was about 40 times greater than that of 2I Borisov, the previous interstellar comet discovered in 2019, whose nucleus was just 0.7 kilometers in size. And even more astonishing, 3I Atlas was at least 20,000 times more massive than the mysterious object Oumuamua, which was barely 200 meters long. These numbers weren't just incremental differences, they were orders of magnitude apart. This massive increase in size wasn't just a statistical curiosity, it had profound implications for how we understand the population of interstellar objects in our galaxy. The large size of 3I Atlas pointed to something far more significant than just the physical dimensions of the object itself. It suggested that interstellar objects, including comets, could be much more common and diverse than we had ever imagined. It also indicated that our solar system might have been visited by objects from other star systems much more often than we previously thought. The discovery of 3I Atlas and the determination of its size changed the way we view space. It showed that our solar system is not isolated, but instead it is part of a vast, interconnected cosmic system receiving material from other systems that have been traveling through space for billions of years. This discovery brought with it more questions than answers. What does the size of 3I Atlas tell us about the early history of our solar system? Could the chemical composition of objects like 3I Atlas hold clues about the origins of life itself? To answer these questions, we need to dig deeper into the process that led to the discovery and measurement of 3I Atlas. The journey to accurately determine the size of this object reveals how challenging it is to measure an interstellar object. The first difficulty in measuring 3I Atlas was the coma, the cloud of gas and dust surrounding the nucleus of active comets. The coma can stretch out hundreds of thousands of kilometers from the nucleus, dwarfing the small, solid core hidden beneath it. When scientists first imaged 3I Atlas in July and August of 2025, they could only see the coma, and the nucleus itself remained hidden. The team, led by astronomer David Jewett, could only establish rough limits for the object's size, ranging from 440 meters to 5.6 kilometers. But these estimates, though a step forward, were not precise. The coma's brightness added another layer of complexity. To isolate the nucleus and measure its size, astronomers had to subtract the coma's glow carefully, a technique that required a high level of precision. This task was made even more difficult by the fact that 3I Atlas had already passed its perihelion, the point in its orbit closest to the Sunday. As the object neared the Sun, its coma grew brighter and more extensive, making it nearly impossible to observe the nucleus. However, as the object moved away from the Sun, the coma began to shrink and dim, and scientists were able to refine their measurements. By late November and December 2025, Hubble returned to the object and used a method known as point spread function subtraction to isolate the faint light from the nucleus. For the first time, a clear signal from the nucleus of 3I Atlas was detected across multiple observations. The result was a nucleus size of 2.6 kilometers, confirmed by both direct observation and dynamic modeling of the object's outgassing behavior. Now that the size of 3I Atlas was confirmed to be 2.6 kilometers, the implications of this discovery became even more striking. When we compare 3I Atlas to its predecessors, the differences are enormous. Let's start by looking at Oumuamua, the first interstellar object ever detected, which was discovered in 2017. Oumuamua's length was estimated to be under 200 meters, and it had no visible coma, no detectable outgassing, and it behaved in strange ways that still remain unexplained. Despite its small size, Oumuamua displayed non-gravitational acceleration, which baffled scientists at the time. Next came 2I Borisov, discovered in 2019. Unlike Oumuamua, 2I Borisov was a true comet. Its nucleus measured approximately 0.7 kilometers across, and it had a visible coma and outgassed water and carbon monoxide. It behaved like a typical solar system comet, which was reassuring because it suggested that comets from other star systems are formed in much the same way as those in our own solar system. But when 3I Atlas came into the picture, it was clear that this object was on an entirely different scale. Avi Loeb's calculations based on the size of 3I Atlas were eye-opening. Given that 2I Borisov's nucleus was only 0.7 kilometers across, and 3I Atlas measured 2.6 kilometers, Loeb estimated that 3I Atlas was about 40 times more massive than 2I Borisov. But the difference in mass between 3I Atlas and Oumuamua was even more staggering. The mass of 3I Atlas was over 20,000 times greater than Oumuamua's. These are not just small differences, they are orders of magnitude apart. 3I Atlas was by far the largest and most massive interstellar object ever detected passing through our solar system. So why does this matter? First and foremost, a more massive object like 3I Atlas carries more material. It contains a greater variety of chemistry, more elements, and molecules that could be crucial to understanding the building blocks of life. When we observed the outgassing from 3I Atlas, we detected a variety of complex molecules, including methanol, HCN, and methane chemicals that are key to prebiotic chemistry. This means that 3I Atlas was not just an object of interest because of its size, but because of the wealth of chemical information it carried with it. The fact that 3I Atlas was so much larger than its predecessors also has important implications for how we detect interstellar objects. If 3I Atlas had been smaller, say 0.7 kilometers like 2I Borisov, it would have been much harder to detect, particularly at the distance it was found. In fact, a nucleus only 440 meters across, as initially suggested, would have been virtually invisible at the distance where 3I Atlas was discovered. This means that for every object like 3I Atlas that we manage to detect, there are likely many smaller interstellar objects passing through our solar system undetected. But the most significant implication of 3I Atlas's size is what it tells us about the population of interstellar objects in our galaxy. With the detection of 3I Atlas, astronomers can now estimate the number of similarly sized objects in the solar neighborhood. These calculations, combined with the size and brightness of 3I Atlas, suggest that there are likely many more interstellar objects like it out there, waiting to be discovered. In fact, we might only be scratching the surface of understanding how common these objects are. As we've established, 3I Atlas is by far the most massive interstellar object ever detected. But why does the size of this object matter so much? The size of 3I Atlas has major implications for our understanding of the population of interstellar objects in our galaxy. To explore this idea, let's break down how scientists estimate the total population of interstellar objects like 3I Atlas. Astronomers use surveys to detect objects like 3I Atlas, and from the detection rate, they can estimate how many similar objects exist in the solar neighborhood. The detection of 3I Atlas by the Atlas survey in July 2025, combined with the survey's parameters and the object's brightness, enabled astronomers to make some astonishing predictions. By applying these models, they were able to estimate that at any given moment there is at least one object roughly the size of 3I Atlas within 4.5 AU of the Sun, essentially between the orbits of the Earth and Jupiter. Let that sink in for a moment. This means that there could be an object as massive as 3I Atlas, originating from another star system, passing through our solar system right now, and we might not even know it. It's a mind-boggling thought. This object could be coming from a planetary system billions of years old, perhaps even older than our own solar system. The fact that it hasn't become active yet, or hasn't passed close enough to be detected, makes it incredibly difficult to spot. It's important to remember that 3I Atlas is far from an anomaly. Objects like it, objects that are massive, complex, and rich in chemistry, are likely more common than we realize. We just haven't detected them yet. The reason for this is simple. The detection of interstellar objects is a difficult task, and smaller objects, like the rocky, dark ones that don't have comas, are incredibly hard to spot. These objects are far less bright and won't develop tails like comets. In fact, if 3I Atlas were only 440 meters across, it would have been nearly impossible to detect at the distance it was found. But the new detection technologies are on the horizon, and this changes everything. The Vera C. Rubin Observatory, which is now operational, is set to revolutionize our ability to detect interstellar objects. Unlike previous surveys, the Rubin Observatory's LSST, Legacy Survey of Space and Time, will scan the entire accessible sky every few nights. It will cover much deeper regions of space than the Atlas survey, and projections suggest that Rubin could detect multiple interstellar objects per year, whereas surveys like Atlas could only detect one per decade. As Rubin's survey begins to detect more and more interstellar objects, we will gain an unprecedented understanding of how the population of these objects is distributed. We will learn about the size, range of objects, how many are large, like 3I Atlas, and how many are smaller. We will begin to see how the chemical composition of these objects varies, whether they contain more complex prebiotic molecules, and how their size distribution compares to that of objects ejected from planetary systems during their formation. With enough detections, we can build a detailed picture of interstellar space, a space that is much more dynamic and full of life than we ever imagined. The implications of this shift in understanding are far-reaching. As astronomers learn more about the size and chemical distribution of interstellar objects, we may begin to understand how our own solar system fits into this larger galactic framework. Are we just another random star system, or are we part of a much larger cosmic ecosystem where material from other stars regularly infiltrates our system? This is where 3I Atlas becomes more than just an object passing through. It becomes a calibration point for all future observations of interstellar objects. It offers a glimpse into the larger reality of space, where stars and planets are not isolated islands, but instead interconnected nodes in a galactic web. Every new object we detect will add another piece to this puzzle, revealing how the materials and chemistry of distant stars influence the evolution of our own solar system. Now that we understand the implications of 3I, Atlas's size, let's explore its chemistry in more detail. The chemical composition of 3I, Atlas, is one of the most intriguing aspects of this discovery. When astronomers first observed 3I, Atlas, they detected an array of complex molecules, including methanol, HCN, hydrogen cyanide, and methane, all of which are crucial to the study of prebiotic chemistry, the chemistry that could have contributed to the origins of life on Earth. These chemicals were released from the coma of 3I, Atlas, the cloud of gas and dust surrounding the nucleus. The methanol alone was found to be 4 times more abundant than the average found in solar system comets. This discovery is significant because methanol is considered a key prebiotic molecule. It can serve as a building block for more complex molecules that are essential for life, such as amino acids. The presence of HCN and methane further adds to the intrigue, as these molecules are often linked to the processes that lead to life's chemical precursors. But it's important to note that the chemistry of 3I, Atlas, is not just limited to the surface. The material detected during the December 2025 eruption was actually from deeper layers of the nucleus layers that hadn't been exposed to solar radiation since the object formed in its original star system, possibly 7 billion years ago. This deeper chemistry is crucial because it suggests that the molecules on the surface of 3I, Atlas, may not represent the full chemical profile of the object. Instead, the full inventory of molecules inside the nucleus could be far more diverse and complex, with richer materials like methane and carbon monoxide that had been shielded from the sun's heat. As astronomers study these deeper layers, they are piecing together a picture of the kind of chemistry that existed in the early universe before our solar system was even formed. The chemical inventory of 3I, Atlas, is not just a snapshot of a single comet, it is a glimpse into the prebiotic chemistry of a system that is billions of years old. This is important because it means that interstellar objects like 3I, Atlas, may have played a significant role in the chemical evolution of other planetary systems, including our own. For instance, consider the possibility that objects like 3I, Atlas, might have contributed to the molecular precursors of life on early Earth. Comets and asteroids have long been thought to have played a role in delivering the organic compounds necessary for life to form. If 3I, Atlas, with its rich prebiotic chemistry, had passed through the early Earth system, it could have delivered critical compounds that helped jumpstart the chemical processes that led to the origins of life. The size and chemistry of 3I, Atlas, make it a cosmic messenger. It is not just a comet passing through our solar system, it is a relic from another star system, carrying with it the building blocks of life. The object's 2, 6, kilometer nucleus, combined with its ancient chemistry, tells a story that stretches back billions of years. It represents a cosmic history that predates Earth itself, carrying with it information that could help us understand how life in the universe is seeded and spread. By studying the chemistry of 3I Atlas, scientists can begin to piece together the larger narrative of how the galaxy has evolved and how the materials necessary for life have been distributed across different star systems. In the end, the significance of 3I Atlas lies not just in its size or its chemical composition, but in what it tells us about the interconnectedness of all planetary systems. It's a reminder that we are not alone in the universe, and that our solar system is just one part of a much larger, far-reaching cosmic system. As we delve deeper into the story of 3I Atlas, it's crucial to step back and understand the broader implications of its existence, not just as an isolated object, but as part of a much larger cosmic web. 3I Atlas is a vivid reminder that our solar system is not an isolated entity. Rather, it is interconnected with countless other planetary systems scattered throughout the galaxy. This object, which traveled across 7 billion years of interstellar space, offers us a glimpse into the past, into a time long before the formation of Earth, and perhaps even before our Sun itself. Think about it for a moment. 3I Atlas is a messenger from a long-lost star system, a time capsule carrying the ancient chemistry of a distant stellar nursery. It traveled through space for billions of years, its nucleus gathering material and chemical information from its home system before eventually passing through our own solar system. The fact that we have detected this object and that it's shedding chemical and physical data about the origins of planetary systems is a monumental discovery. The chemistry of 3I Atlas, from its rich inventory of prebiotic molecules like methanol, HCN, and methane, offers a tantalizing glimpse into the molecular inventory of another star system. This is more than just a comet passing by. This is a cosmic artifact from another time and place in the galaxy. In fact, the chemistry of 3I Atlas is a reminder of how planetary systems evolve, how stars form, and how the raw materials for life itself travel across the vast distances of the universe. The size, chemical composition, and age of this object show that interstellar objects are far more common and far more significant than we ever realized. One of the most profound implications of this discovery is how it challenges our understanding of the solar system's formation and its ongoing interactions with the rest of the galaxy. Objects like 3I Atlas may have been visiting our solar system for billions of years, bringing with them new molecules, new material, and new chemistry. Perhaps some of the building blocks of life on Earth came from objects like 3I Atlas, objects that have been traveling through interstellar space long before our planet even existed. What does this mean for our understanding of the origins of life? Could the complex organic molecules found on 3I Atlas have contributed to the development of life on Earth, or could they have played a role in seeding life on other planets? These are the kinds of questions that are only now becoming possible to answer as our detection methods improve and we study the chemical fingerprints of these interstellar travelers. But the true significance of 3I Atlas goes beyond chemistry. It forces us to rethink our place in the universe. This object didn't just happen to pass through our solar system. It was always meant to, traveling on its path across the galaxy, following the forces that govern the motion of stars and planets. The fact that 3I Atlas is from another star system makes us realize how interconnected the galaxy really is. Our solar system is not an isolated bubble of existence, but a part of a larger cosmic network constantly interacting with objects from other star systems. The universe isn't just a collection of isolated worlds. It's a dynamic, interconnected web of planetary systems, all sharing material and information across vast stretches of time and space. This realization has profound implications for how we understand the origins of our own solar system. The passing of 3I, Atlas, could be just one of many similar events that have shaped the chemical makeup of our system. We now understand that our solar system is not static but is constantly being influenced by the flow of material from other systems. The raw materials of life, the molecules and elements that make up our world, may have traveled across the galaxy for billions of years before arriving here. Perhaps life, too, has been part of this interstellar exchange, carried by objects like 3I, Atlas, from one system to another. While the discovery of 3I, Atlas has revolutionized our understanding of interstellar objects, it also highlights an important issue. Our current scientific infrastructure was not fully prepared to handle an object of this magnitude. Yes, we had the telescopes Hubble, Webb, ALMA, Swift, and Spherix, each performing exceptionally well, providing us with valuable molecular detections, precise measurements of the nucleus, and insights into the object's jet morphology. These scientific triumphs have provided us with a wealth of information about 3I, Atlas, but we still missed out on one crucial opportunity. Despite the remarkable discoveries made from afar, we lacked the capability to send a spacecraft to 3I, Atlas, to study it up close. The Juno spacecraft, which was orbiting Jupiter at the time, could have intercepted 3I, Atlas, in March 2026, coming within 27 million kilometers of the object. This would have provided us with a much clearer and more detailed understanding of its properties. Unfortunately, the Juno mission was not redirected in time to intercept 3I, Atlas, and we were left with only the data gathered from hundreds of millions of kilometers away. Similarly, the Comet Interceptor mission, which has been waiting at L2 since 2024, was designed specifically to study interstellar objects like 3I, Atlas. However, it wasn't positioned correctly to intercept 3I, Atlas. The lesson here is clear. We need to be more proactive. Our scientific infrastructure is advancing, but we are not fully prepared to act quickly when an interstellar object like 3I, Atlas comes into view. We need to have standing plans, pre-authorized protocols, and ready-to-launch missions to intercept interstellar objects as soon as they are detected. The real takeaway from 3I, Atlas, is that the universe is far more interconnected than we ever imagined. Our solar system is not a lonely island, but part of a dynamic, ongoing exchange of material with other star systems. The passing of 3I, Atlas, reminds us of this reality and underscores the need for better planning and quicker responses to interstellar discoveries. In the future, the next interstellar object could arrive at any time, and we must be ready to capture and study it in ways we've never done before. As 3I, Atlas, moves past Jupiter and continues on its journey out of the solar system, the questions it raises will linger. The data we've gathered will help shape our understanding of the galaxy and our place in it. And even though the object is leaving, the conversation is just beginning. We've only begun to understand the vast implications of interstellar exploration. If you're fascinated by 3I, Atlas, and the mysteries it holds, make sure to subscribe to this channel for more updates on future interstellar discoveries. Share this video with someone who thinks 3I, Atlas, is just another comet passing through, and drop a comment below, letting me know what you think about the size of 3I, Atlas, and what it means for our understanding of the universe. Because 2.6 kilometers of interstellar nucleus, 7 billion years old, is more than just a comet passing by. It's a message, and we're still reading it. Stay tuned for more exciting updates